Imagine standing at the edge of a multi-trillion-dollar industry shift, only to discover that every expert, analyst, and major automaker was looking in completely the wrong direction. For over a decade, the promise of electric vehicles hinged on a surprisingly flawed equation. Build a larger battery pack, stuff it into a heavy frame, and hope that sheer manufacturing scale would eventually make it affordable. But behind closed doors, the global automotive apparatus hit a brutal physical wall. Range anxiety was never just a psychological trick played on consumers. It was an undeniable limitation of heavy, expensive, heat-sensitive lithium-ion chemistry that required massive amounts of fossil fuel-intensive energy just to build. Legacy automakers poured hundreds of billions into building legacy battery factories, working under the assumption that the company with the largest facility would automatically win the race. Then, word began leaking from high-security engineering facilities in Texas and Fremont that the underlying playbook had been torn up completely. What engineers uncovered was not merely another small efficiency gain or a public relations gimmick designed to boost stock prices. It was an absolute overhaul of how energy storage is manufactured at an atomic scale, a breakthrough so disruptive that it threatens to render traditional vehicle assembly lines completely obsolete practically overnight. To understand why this development sent shockwaves through global markets, you have to look closely at the dirty secret the battery industry tried to keep hidden for generations. Traditional battery manufacturing is an extraordinarily inefficient, capital-intensive, and environmentally taxing process. To create a standard lithium-ion cell, chemical companies must take active materials and mix them with toxic liquid solvents to create a wet slurry. This wet chemical compound is then sprayed onto massive sheets of delicate metal foil, which are fed through football field-sized industrial ovens that burn immense amounts of electricity just to dry the coating out. These ovens consume roughly 40% of the total energy required to build an electric vehicle battery, while forcing companies to construct sprawling, multi-billion-dollar facilities just to fit the equipment. When news first broke years ago that a major player had acquired a small energy storage company called Maxwell Technologies, rival executives publicly scoffed at the move. They viewed dry electrode coating as an unscalable laboratory experiment that would crumble under the brutal realities of high-volume mass production. Internal leaks painted a bleak picture for years, with reports of ruined machinery, torn foil rolls, and scrapped prototypes leading industry observers to assume the project was dead in the water. That skepticism was precisely what allowed the breakthrough to develop entirely in the shadows. Away from public scrutiny, teams of material scientists and mechanical engineers completely re-engineered the mechanics of dry coating from the ground up. Instead of relying on wet chemical slurries and massive oven arrays, the new process compresses pure active battery powders directly onto metal foil using ultra-precise, high-pressure industrial rollers. By completely eliminating the liquid solvent phase, the physical footprint of the battery plant shrinks by upwards of 70%, while factory energy consumption drops by more than 3/4. But reducing facility size means nothing if the resulting battery cell cannot withstand the grueling physical demands of real-world driving. That is where a secondary engineering miracle occurred that completely caught traditional battery suppliers off guard. When independent teardown experts finally got their hands on early test cells, the internal chemical structure defied standard technical expectations. Without liquid solvents present during the manufacturing phase, the active material layer formed a far denser, structurally resilient matrix that resists microfracturing during rapid charge and discharge cycles. Microscopic degradation has always been the primary reason electric car batteries lose range over time, as repeated exposure to extreme heat and electrical current causes the internal structure to slowly break down. With this dry process architecture, internal resistance is reduced significantly, allowing the battery to handle extreme power demands with a fraction of the heat generation that normally plagues standard cells. But as impressive as these manufacturing efficiencies are, the real panic among competing automotive CEOs wasn't triggered by how the battery was physically built, but by what was happening inside its chemical formulation. For years, the global automotive landscape was held hostage by the surging costs of raw metals like cobalt and nickel. Prices swung violently on international markets, supply chains were tied to politically unstable regions, and vehicle production costs remained firmly locked to volatile commodity exchanges. This new cell generation completely breaks free from those constraints by introducing a high manganese, cobalt-free chemistry that drastically reduces reliance on high-cost nickel. By pairing this refined cathode with a silicon-doped anode capable of storing vastly more lithium ions per unit of volume than standard synthetic graphite, energy density surges while material costs plummet. Internal projections indicate this combination drives the manufacturing cost per kilowatt-hour down past the legendary $50 threshold. In the automotive engineering world, reaching $50 per kilowatt-hour is considered the absolute point of no return, the exact tipping point where an electric vehicle becomes cheaper to build than a gas-powered car without needing a single dime in government subsidies or tax credits. Word of this chemical evolution sent wave after wave of anxiety through executive boardrooms across North America, Europe, and Asia. Legacy manufacturers had built their long-term business models around the assumption that battery costs would decline slowly over decades, projecting price parity with gas engines somewhere near the end of the 2030s. Suddenly, those legacy brands found themselves locked into long-term supply agreements for older battery chemistry that costs nearly double to produce. Reports began surfacing of emergency strategy sessions, halted factory construction, and quietly abandoned vehicle programs, as executives realized their upcoming product lines would be completely uncompetitive on price before they even reached consumer hands. And what happened next left supply chain analysts utterly baffled. As legacy automakers scrambled to negotiate contracts for basic raw materials, a silent land grab was taking place right under their noses. Recognizing that cheap battery chemistry is useless if you remain dependent on external refiners, massive capital was poured directly into building domestic lithium processing infrastructure and securing direct extraction rights. By bypassing traditional chemical distributors and constructing state-of-the-art refining facilities close to vehicle assembly plants, raw material transit times were slashed from months down to a matter of days. This closed-loop supply system established a cost barrier that effectively shields vehicle production from international trade disputes, sudden export restrictions, and artificial price manipulation by foreign monopolies. While this supply chain revolution was quietly taking hold, legacy car companies launched massive public relations campaigns designed to convince consumers that a completely different technology was right around the corner. Headlines were suddenly flooded with promises of solid-state batteries, claiming 5-minute charge times and 1,000-mile ranges, while assuring buyers that current electric cars would soon be obsolete. But, behind the glitzy auto show presentations, the technical reality tells a very different story. Solid-state development remains severely bottlenecked by fundamental physical flaws, including the rapid formation of microscopic lithium dendrites that short-circuit cells, extreme sensitivity to ambient temperatures, and production costs that make mass manufacturing virtually impossible for the foreseeable future. While competitors chased headlines with laboratory experiments years away from commercial viability, this dry-coated hybrid cell architecture was quietly transitioning onto high-volume production lines, delivering 80% of the performance benefits of solid-state at a tiny fraction of the cost right now. The impact of this chemical breakthrough stretches far beyond consumer passenger cars. The exact same high-density, low-cost cell geometry is built to scale directly into utility-grade energy storage systems designed to replace aging fossil fuel power plants. Skeptics have long argued that renewable power generation is inherently unreliable, claiming that solar and wind power are useless without insanely expensive grid-scale backup systems. But when the cost of stationary energy storage drops below critical levels, large-scale battery farms become dramatically cheaper to build and operate than traditional natural gas peaker plants. Regional utility companies are already pivoting their long-term infrastructure budgets, replacing legacy power stations with massive battery installations that absorb surplus grid energy during off-peak hours and discharge it seamlessly when demand spikes. This multi-industry manufacturing model creates a compounding economic flywheel that single-purpose car companies simply cannot replicate. While traditional car brands manufacture batteries exclusively for their own vehicle lineups, a multi-use energy strategy ensures that every single cell rolling off an automated assembly line is utilized immediately, whether inside an affordable sedan, a commercial transport truck, or a municipal grid installation. This relentless demand keeps production equipment running at maximum capacity 24 hours a day, driving down unit costs through sheer volume and establishing an exponential scaling advantage that leaves low-volume competitors further behind with every passing week. Inside auto industry circles, quiet conversations are taking place about how traditional vehicle dealerships will survive this sudden shift. For over a century, independent auto dealers earned the vast majority of their profits not from the initial sale of a new vehicle, but from service departments, routine oil changes, transmission repairs, and engine overhauls. A vehicle built around a low-degradation, dry-electrode battery system requires practically zero mechanical maintenance over its working lifespan. The core drive components are engineered to endure hundreds of thousands of miles with minimal physical wear, eliminating the steady stream of repair bills that traditional dealerships rely on to keep their doors open. As maintenance requirements evaporate, the legacy dealer business model faces an existential financial crisis that will fundamentally alter how cars are bought, sold, and maintained. This unprecedented mechanical longevity is set to completely rewrite the financial rules governing the pre-owned vehicle market. Historically, purchasing a used electric car with high mileage was viewed as an enormous financial gamble, with buyers fearing a sudden battery failure that could cost more than the vehicle's total remaining value. But with cell chemistry explicitly formulated to withstand thousands of harsh thermal cycles without significant degradation, a high-mileage electric vehicle retains its usable range and performance for decades. The second-hand car market, which has long been a predatory space for low-income buyers forced to purchase unreliable gas vehicles with high operating costs, will soon be flooded with affordable, virtually zero-maintenance transportation options. Unsurprisingly, a technological disruption of this magnitude has ignited aggressive pushback from powerful economic interests. Energy sector lobbyists, mining syndicates tied to legacy supply contracts, and coalitions of traditional car manufacturers have launched coordinated efforts to stall adoption. They have lobbied regulatory bodies to impose strict new tariffs on processing components and pushed for complex environmental rules aimed directly at halting new refinery construction. There have even been instances where opposition groups tried to weaponize local zoning laws to prevent modern manufacturing facilities from reaching full operational status. But trying to stop an industrial leap forward of this scale through bureaucracy is like trying to protect steam engines by outlawing diesel locomotives. The economic advantages are simply too massive for political friction to contain for long. Consider the choices facing an average consumer stepping onto a dealer lot in the very near future. On one side sits a traditional internal combustion vehicle packed with thousands of friction-heavy moving parts, requiring expensive fossil fuels, frequent fluid changes, complex emission systems, and guaranteed steep depreciation. On the other side sits a vehicle built around a next-generation dry process cell, offering an ultra-low purchase price, rapid charging capability, negligible operating costs, and a drive system designed to outlast the frame of the car itself. The decision is no longer a matter of environmental ideology or brand loyalty. It becomes a brutal financial calculation that makes choosing a gas engine economically irrational for the vast majority of drivers. That stark reality explains the state of quiet panic currently sweeping through legacy automotive headquarters. Legacy brands are caught in a devastating financial vice grip, trapped between falling demand for their traditional internal combustion models and crippling losses on their early-generation electric offerings. Having spent decades outsourcing their core engineering capabilities to third-party suppliers, these legacy giants lack the internal software and chemical expertise required to retool their assembly lines for dry electrode manufacturing. They find themselves stuck with massive debt loads, stranded asset investments in old engine plants, and union labor contracts that make rapid operational pivots virtually impossible to execute. As these high-speed assembly lines run continuously and production yields tick upward week after week, the broader economic ramifications are becoming impossible to ignore. We are approaching a historical inflection point where power generation, freight logistics, personal mobility, and municipal energy infrastructure converge into a single electrified ecosystem driven by cheap, ultra-durable energy storage. The dominoes are falling at a rate that catches traditional economic forecasters off guard, completely disproving long-held assumptions about how quickly global transport systems could transition away from fossil fuels. The former era of automotive dominance was built on precise engine machining, complex fuel injection, and intricate multi-speed transmissions that took a century to perfect. That entire mechanical paradigm is being rendered obsolete by a tightly integrated array of dry-coated cells mounted low within a vehicle chassis. The struggle to control the future of transportation was never going to be decided by vehicle styling, interior leather choices, or flashy dashboard screens. It was decided deep inside chemical laboratories and automated production plants, where engineers successfully cracked the code on dry powder processing, delivering high-density energy storage faster, cheaper, and at a scale the world had never seen before. The debate over whether electric power will completely replace the internal combustion engine is officially over. The outcome was sealed the second this new manufacturing architecture demonstrated its viability at full production volume. The only remaining question is how many historical auto giants will go bankrupt before they manage to adapt, and how dramatically global energy markets will be restructured as hundreds of millions of long-range vehicles and stationary storage blocks begin taking over the world's power grids. The ground beneath the transport industry has split wide open, and the structural transformation now underway will reshape global commerce for decades to come. What makes this mechanical shift even more compelling is the way it radically lowers the barrier to entry for full fleet automation and shared mobility services. For years, major technology companies and ride-hailing platforms worked on autonomous driving algorithms, assuming that software was the primary hurdle standing between us and cheap, automated transportation. But fleet operators quietly faced a massive physical problem that software alone could never solve: operational cost per mile. An autonomous vehicle fleet operating 24 hours a day would rapidly incinerate standard lithium-ion batteries through constant fast charging and non-stop drive cycles, requiring expensive pack replacements every couple of years that rendered the unit economics completely unsustainable. With a dry-coated, high-cycle battery structure designed to endure over 1 million miles of continuous operational stress, the hardware foundation for autonomous transport networks is finally locked into place. When you combine a battery pack that lasts for 1,000,000 miles, with a vehicle drivetrain that requires no maintenance, and a fuel cost that drops to fractions of a cent per mile, the cost of automated transport drops below the cost of owning a personal automobile. That economic reality will spark a profound shift in urban centers, as millions of city dwellers question the financial logic of paying thousands of dollars a year for car payments, insurance, parking, and fuel for a vehicle that sits parked 95% of the day. The rise of cheap, long-life cell manufacturing is the invisible key that unlocks the door to a world where on-demand autonomous transit becomes a universal public utility, drastically reducing traffic congestion and freeing up vast amounts of valuable urban space currently dedicated to parking structures and gas stations. As this supply wave scales globally, traditional oil refining conglomerates are waking up to a terrifying long-term reality. Historically, petroleum executives operated under the assumption that while passenger cars might slowly transition to electric power, heavy transportation, long-haul trucking, commercial shipping, and industrial power generation would remain firmly dependent on liquid fuels for decades due to energy density requirements. But the emergence of ultra-dense dry process batteries directly targets those high-demand commercial sectors. Heavy transport trucks equipped with high-voltage, low-cost battery architectures are already demonstrating superior total cost of ownership compared to diesel rigs, offering instant torque, lower brake wear through regenerative braking, and fuel cost savings that save fleet operators tens of thousands of dollars per vehicle every single year.